Hello everyone, how are you? I hope you are all doing well. So today in this video, we will study magnetization and magnetic intensity. Okay, so basically, we will study that what is magnetization, what is magnetic intensity, and what is the correlation between magnetization and magnetic intensity, and how it works. Like what in like CBSE board exams, one question definitely sometimes comes from this topic like magnetization and magnetic intensity. There is a proof, like there is a lengthy proof for like one equation B equals to mu h that we are going to derive here. So in that first term is magnetization. So what is magnetization? Magnetization is the net magnetic moment per unit volume. Okay, so whatever magnetic substance we are taking here, so of that particular magnetic substance, the net magnetic moment per unit volume is called as magnetization, and it is denoted by capital M vector. Let me write magnetization, and it is denoted by capital M vector. Okay, it is the net magnetic moment, and I'll describe that why it is net magnetic moment. Net magnetic moment per unit volume, and it is given by m vector equals to m vector net upon volume V. So that's how we represent the magnetization of a particular substance. Okay, now let's come to the point that why we are using here word the net magnetic moment, because we know that in a particular magnetic stance there will be a lot of magnetic moments, and it is not necessary that they all be in the same direction. So they may have their different directions. So because of that, we have to take the net magnetic moment, where the net magnetic moment will be nothing but sum of all the magnetic moments. So here, let me write m net equals to sum of all the magnetic moments, whatever is there. Okay, so sum of all the magnetic moments, if we add all the magnetic moments, so whatever the we can say five, after the sum of all the magnetic moments, whatever quantity we will get, that will be called as net magnetic moment. So that's about the magnetization. And secondary thing is magnetic intensity that we are going to introduce throughout the derivation. So first of all, let's assume that here we have a solenoid, and one soft iron core is inserted into the that mag uh, that solenoid. As you can see in the above diagram, that the blue one, the we can say here the solenoid has n turns per unit volume. So sorry, n turns per unit length. And turns per unit length is the number, we can say the number density of the solenoid. And here the black color, or we can say the black color cylinder, is the soft iron core that we have inserted into the inside the solenoid. So what will be the effect of that? First of all, when the current start flowing here, let's see, if the current I is flowing through the solenoid, what will be the magnetic field due to that? As we know that the magnetic field due to a solenoid is B equals to mu naught Ni. So that will be the magnetic field due to solenoid. But the things doesn't stop here, because we know that the the substance, or we can say the object which we are inserted, which we have inserted inside the solenoid, that is of a magnetic property, that has magnetic properties. And if we talk about the uh, iron, so it is a ferromagnetic substance, so it will get magnetized. Okay, it will get magnetized. Why? Because when there will be a magnetic field, there will be a external magnetic field, because we know that it is inside the solenoid, so it will be experiencing a magnetic field due to the solenoid. And that magnetic field is going to magnetize the soft iron core. And because of that magnetization, we will get one magnetic field. So that's all we are going to see. So here, first of all, the magnetic field, if uh, let's one second. What will be the direction of a dimension of magnetization? It will be, let me write, the dimension of the magnetization. It is ampere meter inverse, or in terms of L inverse A, where L inverse is the meter inverse and A is the ampere. So its dimension is, or we can say unit is ampere meter inverse, because we know that the dimension of, or we can say the unit of magnetic moment is nothing but ampere meter square, and the dimension of volume will be meter cube. So finally we will get ampere meter inverse. Now, if there are uh, if if the solenoid has n turns per unit length, then magnetic field due to it. What will be the magnetic field due to a solenoid? We all know that it is mu naught Ni. This will be the magnetic field due to a solenoid. So now here the total magnetic field will not be just because of the solenoid, it will be because of the magnetization also. So the total magnetic field here, let me write, here the magnetic field total magnetic field is B vector equals to B naught vector plus Bm vector, where we can see that the B naught vector is due to the solenoid, and what is the Bm vector here? It is the magnetic field due to the magnetic material. Okay, so let me write here. Here Bm vector is the magnetic field contributed by the magnetic material core, or in this case we have taken soft iron core, so it will be the magnetic field due to soft iron core. Now there will be a relation between magnetic field due to the magnetization, so obviously we can write that Bm equals to mu naught m vector. Okay, and now the things comes in picture, the magnetic intensity. Okay, how to describe the magnetic intensity? So magnetic intensity is given by, it is the, we can say, it is the another form of new variable here, so that will be denoted by h vector. Now the magnetic intensity magnetic intensity, H vector is expressed as, there is a new quantity magnetic intensity that can be expressed as H vector equals to H vector equals to B vector upon mu naught minus M vector. So this will be the magnet expression for magnetic intensity. That, like, we have one another variable magnetic intensity, and that can be described by H vector equals to B vector upon mu naught minus M vector. Now let's simplify this equation. Then we will get, multiply both of the side by mu naught. So we will get mu naught H vector equals to B vector minus mu naught M vector. So finally we will get B vector equals to mu naught H vector plus mu naught M vector. This equation we will get. And if you see here, the we can say the unit of magnetic intensity is also ampere meter inverse. Ampere meter inverse, because we know by the algebraic equation we can see that the unit of magnetic intensity and the magnetization will be same. Now we know that the magnetization and the magnetic intensity is also related somewhere. And how it is related, that we will see. Both are proportional to each other. Okay, and we'll see as we know what as we know that the as we know that magnetization is proportional to H vector, and later on we get to know that M vector is chi times H vector, where what is chi? Chi is the magnetic susceptibility. Okay, here chi is magnetic susceptibility of the magnetic material. Okay, so now we will put this expression into the above equation. So we then finally we will get B vector equals to mu naught times H vector plus mu naught times chi into H vector. Now we can take H vector common here, and H vector, sorry, mu naught into H vector, we can take it common. So the equation will become as B vector equals to mu naught times 1 plus chi into H vector. So this will be the equation. And remember that this equation is valid for when okay, the medium inside the solenoid is vacuum. Okay, this equation is valid for vacuum, where mu naught is the permittivity of the vacuum. And now we can name 1 plus chi with another constant, because the chi is also a constant value and it does not contain any dimension. The chi is a dimensionless quantity. So let me write here. This equation will be written as mu naught times mu r into H vector. This equation is also important. So let me mark it. Okay. Now Let's describe that what is mu r here. Mu r is 1 plus chi, and it is named as relative magnetic permeability. Okay, it is similar to the in the electrostatics we study that relative permittivity. Okay, so in the similar way in the magnetism we study that it is relative magnetic permeability of the material, or we can say of the of the medium. So whatever medium will be there, according to that we will get the relative magnetic permeability. Now this equation can be reformed as B vector. It can be written as B vector. B vector equals to B vector equals to mu times H vector. And we will see that what is mu here. Okay, so here mu can be written as mu equals to mu naught times mu r. So this is the simple equation we use. Okay, where we can say that the permeability of the vacuum, or we can say free space, and and the relative permeability, both are multiplied here, and this quantity is called as magnetic permeability of any material. Okay, so it can be written as magnetic permeability of magnetic medium. Okay, so it can has different values. For example, if for example for any medium, if the relative permeability is 2, then the value of mu will be 2 mu naught. It is not always mu naught. Sometimes student get confused between, the equation is always B equals to mu naught times H vector. It is not, because mu naught is the equation will have B vector equals to mu naught times H vector when there is a vacuum, or we can say in free space, then only it is possible. But if there is a magnetic medium, for example, where the value of mu r is not 1, it is something else. For example, it is not 1, it can be 2, 3, 4, anything. But in that case we cannot directly write that the magnetic field is B vector equals to mu naught times H vector. Then we have to write this equation only, B vector equals to mu times H vector. So this is all about this derivation. And now if you have any doubt, then you can ask in the comment section.